Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss approximating values using interpolating polynomials. Now, we've already seen interpolating polynomials. However, in this topic we're going to discuss how to design interpolating polynomials. We will observe that we can minimize the condition number of the system that must be solved to find the interpolating polynomial, and consequently we can see how we can optimize these interpolating polynomials so as to make sure that they work well with Horner's rule so as to minimize any introduction of numeric error. Consequently, we will find interpolating polynomials that estimate the values towards the middle of either 2, 3, or 4 points, and then we will find interpolating polynomials that estimate the values closer to the most recent of either 2, 3, or 4 readings. We will also discuss that we should not be using interpolating polynomials for extrapolation, and we will be implementing these in C++ online. So to begin, remember that we've already discussed how in engineering we generally are going to be looking at data that has been periodically sampled from sensors and or possibly other devices. So throughout this section, we're going to assume that our values are sampled equally in either space or time. Now, later on, there are other techniques such as finite element methods, which are beyond the scope of this course, which will allow you to have non-equally spaced points. But that requires significantly more computing power and a lot more linear algebra. So, for this course, we will assume that our values are equally spaced. So the form x sub k being x naught plus k times h, where h is the distance between x values, or some time t sub k is equal to some initial time t naught plus k times delta t. We are also going to assume in this particular talk right now that the values that we are reading are reasonably exact and therefore will be represented by the actual function evaluated at the point. For example, f at x sub k or y at time t sub k. We're also going to be making sure that the polynomials we design are optimally designed so that they can be evaluated using Horner's rule in such a way that minimizes numeric error. Later, we're going to then look at other techniques that can be used if there is significant error in the readings, or if we want to, for example, extrapolate to a future term. Given the state right now, what's the state going to be one time step into the future? Now, suppose that we have the following 2 points, and we'd like to estimate the value of the function somewhere between those 2 points. However, we only have the sampled values at x sub k minus 1 and x sub k. Now, just to remind you, instead of using x sub k minus 1, we could just use x sub k minus h. However, we will be using the first notation here. So if we are trying to estimate the value of the function at some point between these two x values, well, one possibility is just find the line that interpolates those 2 points. And then if we find that linear polynomial, then we can evaluate the function on that interval. Well, if you were to set up the system of linear equations for these points here, it's just a system of 2 equations and 2 unknowns, you would find the coefficients that we present here. Okay, reasonably straightforward. However, there are significant issues with this representation. So what are the issues if we use the interval as we show here? Well, first of all, nothing prevents either of these values from being arbitrarily large. But remember that if we add a large number onto a very small number, we may swamp something out. Alternatively, if two of the values are large, then we're taking a lot of subtractions and we could end up with significant loss of precision due to subtractive cancellation. So that's the thing. There are numerous subtractions here and we'd like to avoid that as well. So here's a solution. Let's try something a little different. Instead of having the points x sub k minus 1 and x sub k, let's choose different x values, negative 0.5 and 0.5. And through this, we will have the same y values, or in this case, f at x k minus 1 and f at x k. And through this, we will find an interpolating line of the form a sub 1 times a new variable delta plus a naught. All right, to do so, we set up the van der Molen matrix, which is a lot easier now. And when we solve this, we get this reasonably simple expression. So we have delta multiplied by the difference of the f values plus the average of the f values. Okay, that's nice. We now have the equation of that line that passes through those 2 points. But it's going from negative 0.5 to 0.5, not x sub k minus 1 to x sub k. So what do we do now? Consequently, if we go back to our original x values, suppose we want to evaluate this interpolating line at some point between x sub k minus 1 and x sub k. Well, what we do now is we determine that x value relative to the midpoint. So basically, we find the value of x that we're attempting to evaluate the polynomial at relative to x sub k minus 1 plus x sub k all over 2, that is the average or midpoint, plus delta times h. Notice that if delta is equal to 0.5, that expression works out to x sub k. If delta is negative 0.5, it works out to x sub k minus 1. Consequently, every single value of delta between negative 0.5 and positive 0.5 expresses some point on the interval from x sub k minus 1 to x sub k. So basically, now when you're programming your embedded system or whatever other system which is using this data, you have to always program it to think in terms of the proportions of the step size. How much are you away from the midpoint relative to the step size? Now, this is actually useful because now look what we have here. We're guaranteed that delta is a value between negative 0.5 and 0.5. So whatever the difference of the f values is, it's multiplied by something that is less than 1 in absolute value plus the average. The second is not subject to subtractive cancellation, and if the difference in the f values is negligible anyway, it doesn't matter because it says there's essentially no slope. So we're taking a slope, multiplying it by a value that's guaranteed to be less than or equal to 0.5 in absolute value, plus another value that's not subject to subtractive cancellation. Consequently, you'll notice that this is exactly what we did with Gaussian elimination with partial pivoting. We swapped rows so that we never multiplied anything by a value that was greater than 1 in absolute value. There's also a nice observation. The condition number of the previous matrix we saw is very, very small. It's only 2. So, for example, suppose that the two x values are 853.4 and 853.5, and the two y values are 9.2 and 9.5. Thus, in this example, we have that the midpoint between the two x values is 853.45. The step size is h is equal to 0.1. The polynomial is therefore 0.3 times delta plus 9.35. All right, so let's pick a value between these 2 points, such as 853.4724. Now, you'll notice that this is equal to the midpoint plus h times the delta value of 0.224. Therefore, in this case, substituting this value of delta, which is less than or equal to 0.5 in absolute value, we have 0.3 times 0.224 plus 9.35. This gives us an approximate value of 9.4172. Next, let us assume we want to approximate values of the function f around the point xk, and we now have 3 values, x sub k minus 1, x sub k, and x sub k plus 1. So points around x sub k on either side, plus or minus h. Now, if you were to actually try to find the interpolating polynomial between these 3 points with those 3 x values, this is what it looks like. Right, that's going to take a while to code if you code it correctly, and yeah, we've got a lot of subtraction going on there. I don't think this is going to work. Let's not do it this way. Instead, we're going to use the same trick we saw previously. We're going to rescale and shift towards the origin. So we want to approximate values of the function around x sub k. If we want to approximate a different value of x outside this interval, that is xk plus or minus 0.5 times h, then we would choose our polynomial around 3 different points. So we're going to focus on x sub k. So instead, we're going to do the same thing we did previously. We're going to find an interpolating quadratic that passes through these 3 points. The x values are -1, 0, and 1. Well, actually, technically, they're delta values. And we have the same f values from the original 3 points. All right, now we have much simpler x values, and to find the interpolating polynomial with these 3 x values, we need to solve this easier system of 3 linear equations in 3 unknowns. If we do that, this is our interpolating polynomial. You'll notice it's a lot easier than the previous version on the last screen. And once again, we will use this polynomial evaluated at delta, where delta goes between -0.5 and 0.5, to approximate the original function at the point xk plus delta times h. So why is this again beneficial? Well, once again, we're guaranteed that we're only going to approximate values within 0.5 times h of the original value x sub k, which means that for this polynomial, we're going to evaluate it at values of delta that are less than or equal to 0.5 in absolute value. Thus, we now have something that's ideal for Horner's rule. Because notice what's happening. I've taken the previous polynomial, rewritten it in terms of Horner's rule. So first we have the coefficient a2, or the coefficient of delta squared, times delta plus the coefficient of delta, all times delta, plus the value of the function. Notice that each time we multiply by delta, we are multiplying, just like with Gaussian elimination, a value that is less than or equal to 0.5 in absolute value. So that essentially means that the new values being added onto the value of f at x sub k, nominally probably a good approximation already of the value of the function, that will not get swamped out, or even worse, made to disappear due to some form of subtractive cancellation if the other coefficients are very large. This doesn't happen anymore, or is significantly less likely to occur. All right, let's look at this other example. Let us assume we are trying to approximate values around the midpoint here, 1025.014. Now, for this problem, we have therefore that the midpoint is 1024.014. The step size is 0.02. However, despite the small step size, because we normalized the values, the x values, so that they are in terms of delta, -101 instead of 1024.012, 1024.014, etc., we get a very clean, straightforward polynomial, 0.15 delta squared plus 0.35 delta minus 0.1, which is, of course, the value of the middle, the value at the midpoint. So let's assume we want to approximate this at 1024.01346. Now, we know that this is the midpoint plus the step size times -0.27. -0.27 clearly indicates that, yes, it is within half a step of the point that we are assuming is the center. If we substitute this into our polynomial, we get the value -0.183565, which is probably quite reasonable. Now, incidentally, if you were to just find the interpolating polynomial without shifting or scaling, what you'd end up with is this interpolating polynomial here. That would be, well, 37,000. That's already large. Second number is 77 million. That's getting pretty large. And that last number looks like it's almost for 40 billion. What's the probability that subtractive cancellation or some sort of other numerical error will not occur if you happen to have an arbitrary choice of x? It would be reasonably difficult to state with certainty that you have not introduced a significant amount of error and lost a significant amount of precision. Finally, let's assume that we are trying to interpolate 4 points. Now, once again, we're going to only interpolate points between the two intermediate values, or the two middle values. The error is smaller on this interval. If you wanted to interpolate between x sub k and x sub k plus 1, you should then use those two values together with the two values around it. So the important point is we want the points we are approximating as close as possible to the center. This will give us the most accurate answer. Now at this point, if we actually tried to just find the interpolating polynomial in x, the interpolating polynomial formula is just too large to show on the screen. We won't even bother. However, as before, we're going to shift and scale. So now we will interpolate these 4 points. The values of the function are the same, but now the x values are negative 1.5, negative 0.5, 0.5, and 1.5. Now, creating the van der Monde matrix, we can find that the solution to this is this formula here. Of course, you're not memorizing this formula, but this formula is one that you can easily program. And what's nice about that is once it's programmed, you don't have to worry about it anymore. Now, at any time, given 4 f values, you can interpolate the function, the 4 points actually, between the two intermediate points with any value delta. Remembering that this polynomial approximates the function f at the midpoint plus delta times h. So the above polynomial is in delta, not in x, as before. So let's take a look at this example. We've got historical data that's perhaps recording temperature once every 2 minutes or 120 seconds. Now, if we wanted to estimate a temperature on the interval from the second point to the third, we note that the midpoint between these two is 106,100. The step size is 120. The interpolating polynomial, once we reset the values, normal and scale them, is now this reasonably straightforward polynomial. If we wanted to estimate what the temperature was at, say, 3 seconds before the third point, then we'd note that this is essentially just the midpoint plus the h value, 120, times 0.475. Evaluating this using Horner's rule, we get that the temperature is approximately 22.11, which is reasonable, I would believe. Now, in the previous question, we've more or less assumed that we have information about the value of the function on both sides of x. However, suppose that these are readings that are taken periodically throughout time, and we are currently at the last reading that was taken. So we are now at time t sub k, and we'd like to know some information about the function. So this is where we are right now. This is the last reading that we have just taken, and we may want to interpolate a few values. Now, the question is, do we want to only approximate values that were in the past, that is, before time t sub k, or may we want to extrapolate and estimate values in the future, say at time t sub k plus 1. What happens one time step into the future? What is an estimate as to the value of y one time step into the future? Unfortunately, if you are finding an interpolating polynomial of degree n between these n plus 1 points, The error is okay inside that interval, but the error grows very rapidly. In fact, if you were to use an interpolating polynomial, even a linear interpolating polynomial, to estimate the value at the next time step, so just one time step into the future, that's actually going to have an error that is a minimum of 8 times larger than any estimate on that last interval you're looking at. And it grows much more so than just 8 times if you're using a cubic or even higher degree polynomial. Consequently, we will use interpolating polynomials to only estimate values in the previous time step. So let's say we've had 2 previous readings or 3 previous readings, and we'd like to know what happened half a time step into the past from the current time. Did we, for example, reach a local maximum or minimum? Now, for just 2 points, we get exactly the same formula as we saw previously for the centered formula for 2 points. So we're going to look at quadratic and cubic interpolating polynomials, taking the last 3 points and the last 4 points respectively. As before, we are going to shift and scale so that the values of delta will fall between negative 0.5 and 0.5, therefore giving reasonable values when we finally apply Horner's rule. Now, given those last 3 points, 0.5, negative 0.5, and negative 1.5, we can write down the van der Monde matrix that we would have to solve. If we solve this, we get the coefficients we see here. Again, reasonably straightforward. Now, this formula is going to approximate values that fall between the last 2 time values, so the average of them, plus or minus delta times delta t, where delta t is the time step between the two between successive readings. The values of little delta will fall between negative 0.5 and 0.5, thus making it useful for Horner's rule. As before, we can also find an interpolating cubic if we use the last 4 time values to find that interpolating cubic. And once again, we center the last interval around 0, and therefore we can estimate the value of the function within the last time step. Once again, you would never really want to evaluate this polynomial for values of delta greater than 0.5, as that would be extrapolating into the future, and that would significantly increase the error. So this is not the approach we will use to estimate what's going to happen one time step into the future. However, this is reasonable, assuming that the values of y are reasonably accurate, to estimate values within the last time step. So here's an implementation of a C++ class which takes the last 4 y values and calculates the interpolating cubic that passes through those points. You can then call the evaluate function that evaluates this interpolating cubic at the appropriate value of delta. Now the constructor simply assigns the array of 4 coefficients in the initialization sequence. And so if you go back to the previous slide, you will see that the coefficients you see here are those coefficients that were listed on the previous slide. Then, inside the evaluate function, we first assert that delta falls between negative 0.5 and positive 0.5, and then, if this is true, it returns the polynomial evaluated using Horner's rule. All right, so it's reasonably straightforward, and what's nice about this is this implementation does not care what the value of delta t is. Is delta t 1 second, our samples being taken once a second? Is delta t 0.001 or 1 millisecond? Or is it once an hour or 3,600 seconds? It doesn't matter, because in your code, when you call the evaluate function, you will simply determine how far in you are relative to the time step, as opposed to the absolute time step or value of t that you're evaluating at. So this is nice. This is completely independent of any time step. It just assumes that you have the last 4 y values and you'd like to estimate the value of the function in the most recent time interval. So, following this topic, you now understand that we can find interpolating polynomials that are specifically designed to minimize the condition number and be appropriate for use in Horner's rule, and consequently minimizing numeric error. You also understand how to use 2, 3, and 4 points to estimate values in the middle of these equally spaced points. And you also understand know how to use the last 2, 3, and 4 points to estimate values in the most recent time interval. You also understand that we will not be using interpolating polynomials to extrapolate values in the future. For that, we will see other techniques. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!